This episode of the HVAC School Podcast is made possible by our sponsors. One of those sponsors being Carrier and Carrier.com. Thanks to Carrier for investing in technician training by investing in the HVAC School Podcast. Also, thanks to Refrigeration Technologies at Refrigetech.com. I've talked a lot about them, and hey, they make Big Blue, okay? Haven't used Big Blue, then what's wrong with you? Big Blue's good stuff, finding leaks. If you are brazing and pressurizing and not bubble testing your joints, then you need to start doing it, and you should use Big Blue. Also, Aeroasis, aeroasis.com/go for you to find out how you can use Aeroasis in your company for indoor air quality products. They're American-made, no-nonsense IAQ company, the company I've been looking for many years, the one that's not full of fluff, but rather it just makes good quality indoor air quality products. That's aeroasis.com/go. Also, Navac at navacglobal.com. You can buy Navac products now at trutechtools.com, trutechtools.com. Offer code GETSchooled for a great discount. I'm especially enjoying the NRP 8DI vacuum pump and the NEF 6LI flaring tool. Those are two tools that I've been using recently, and I really like them. They make a lot of different types of things. They make scales, recovery machines, leak detectors, swedge tools, all that kind of stuff, and you can find it all at TruTech Tools.
Here's the guy who talks about Testo 605Is and delivered capacity in his sleep. And maybe Jim Bergman. But he swears it was just one of those, I'm flying and my friends were all there sort of dreams. Nothing weird. Brian Orr.
Hey, you found the HVAC School Podcast. You are one of the few, the proud, the HVAC School Podcast listeners, one of the ones who wants to learn more about some things that you might have forgotten along the way, as well as remember some things that you forgot to know in the first place, and good on you for doing it. Today, I'm talking to Chris Stevens, and we're talking about commercial refrigeration temperature controls on the basic side. We're not going into the really fancy stuff, just the basics of commercial refrigeration temperature controls, and those are one of the first things if you're going to be working on a refrigeration system, and you are mostly an air conditioning technician, that you may be a little thrown off by, so hopefully you'll find this helpful. So here we go. Chris Stevens, talking refrigeration temperature controls. All right. Thank you, Chris, for coming on the podcast.
Thank you for having me.
Chris has written for the HVAC School website, written some tech tip articles, and this particular podcast that we're doing is sort of based loosely around an article that he did on reach-in temperature controls. It's interesting because as simple as temperature controls are, or refrigeration controls are, there's a lot of questions about them, and I think it stems from the fact that the way that they function is so different than the way that we do air conditioning controls, even just from the voltages and everything. So I think that's where a lot of that confusion comes in. So I like to hit on these topics because I know a lot of you are obviously air conditioning technicians primarily, and it's just good to kind of get a refresher. So some of this is going to be really basic for some of you, but I think some of you it'll be a good refresher, maybe even for your first introduction into it. But before we even go into that, just tell us a little bit about you and what you do, about your company and the type of work you do.
I'm a service technician here in Southern California. I call myself a service technician. I'm technically a part owner in a service company here. We're a commercial refrigeration company that specializes in restaurants. So I'd say 98% of my work now is restaurants. So I work on reach-in refrigerators, ice machines, air conditioners. I work on it all pretty much. I've been in the trade for over 15 years. I kind of lose count. So I'm also very much involved in my local RSES chapter here in Southern California. It's actually the Arrowhead chapter. I actually joined that chapter because I wanted more information about the industry. I wanted to increase my technical skills and be able to talk with other peers that work in the industry. And that is something that RSES really does help out with. I think that it's definitely a lot easier to find information about the industry now with all the YouTube pages and HVACR school. The information is actually a lot easier to get than it used to be. And with that being said, I actually started a YouTube channel also. The start of my YouTube channel was actually for my employees. It really wasn't to post the videos and make them public. They used to be private. And I would just film the things that I thought were interesting that I used to talk to the guys about. I figured, hey, I've got a camera phone, so why not start filming them? That kind of worked out for the guys really well, so I just decided to make it public. And so now I have a YouTube page called HVACR Videos, and I post videos about just the interesting stuff that I see. Reach-in refrigerators. There's some good examples of misdiagnosis in there from myself and from other technicians.
There you go. And that's actually a very similar story to how HVAC school got started. Same thing. I started creating stuff for my own employees and then thought I should just put that out there just to benefit the industry. And then it turned into something. So for those of you who don't follow Chris's channel, it's a really, really great channel. And we're going to mention it again at the end, but if somebody wants to look it up, what's the name of the channel?
It's called HVACR Videos.
Yeah, it's an excellent channel. It's in my 2 top favorite channels that I watch and that I use with my employees. It's you and AK Greaves or AK HVAC. Those are the 2 channels that I enjoy the most. So well done on that.
Thank you.
So let's get into these controls here. So let's start with just talking about temperature controls and how they differ from HVAC controls, or AC controls, I should say, air conditioning, thermostats. What are some things that can make them different?
Well, I would say the biggest thing is just the temperatures at which we're controlling. I mean, when you're looking at a standard air conditioner, what are you looking at? Like 45 degree evaporator temperature, 55 degree evap temp? Is that about accurate?
Yeah, I mean, anywhere from a 35 degree evaporator temperature at the very coldest up to, maybe 55 if you're under really high load or something like that.
Yeah, so on the refrigerators, we're basically just bringing the box temperature down. We're trying to keep legally, federal law says we have to keep our product temperature under 41 degrees for a refrigerator. So with that being said, you've got an evaporator TD that is going to be a lot lower than that box temperature, typically 20 to 25 degrees below the actual box temperature. So if you're running a 40 degree box temperature, subtract 25 from that, and you've got a pretty low evaporator temperature. So a lot of these controls are essentially just bringing the box temperature down. Now, I will say that unlike an air conditioner, the refrigerators oftentimes will disconnect the compressor directly instead of running it through a thermistor. Instead of running it through contactors. That is something that is changing slowly, but you can get some of these basic, simple coil sensing temperature controllers that literally the power wire for the compressor runs right through the control. There's really not a lot different about an air conditioner except for the temperatures at which we're controlling.
But you do think a little bit differently about evaporator temperatures, coil temperatures, that sort of thing. And you stated it right off the bat when you talked about TDs. Whenever we say TD in air conditioning, Jim Bergman and I have been working with techs to try to get them to think differently about this. But a lot of times, techs automatically think of delta T, which is the difference between the air temperature going into an evaporator coil versus out of an evaporator coil. And they don't necessarily always think of their suction saturation, which is what we compare for superheat. That's the temperature we use for when we measure superheat. They don't necessarily think of that as the evaporator temperature. Whereas in refrigeration techs have a much better sense of that your suction saturation pressure correlates to an evaporator temperature, or they're measuring the evaporator temperature directly. And it's that difference between that evaporator temperature and the temperature of the air entering the evaporator, i.e. the temperature of the air in the box, that refrigeration technicians think of quite a bit.
I would definitely agree with that, but I also don't make us sound to be anything special. We're just technicians and we make the same mistakes as everybody else. I would say that a lot of the videos that I've made, I'm pretty honest in my videos that a lot of the examples and advice that I give is because of the mistakes that I've made. I've made a lot of mistakes. Luckily, there wasn't severe consequences for those mistakes, and I corrected them and righted them with the customer, but I learned from them. We're just normal people. We're the same as everybody else. I mean, I work on air conditioners just the same as I work on refrigerators. I will say, though, that you pointed out a good thing about the TD in that people tend to confuse that with the delta T. That is something that even confused me when I was in trade school because I would go at nighttime. So I could literally have one class where I was taking an air conditioning class and the teacher was talking about delta T, but he kept calling it a TD. And then the next day I'm in a refrigeration class and he's talking about the TD. And I would question, like, what do you mean? And then I would get frustrated when we would take a simple test and I would get the answer wrong. And it's like, well, wait. So it is very easy to get confused on the two. I think even with air conditioning, if you can stop looking at pressures, and when I say stop, I mean, you're still going to consider your pressure. But if you start looking at saturation temperatures, it's going to make your life a lot easier.
I agree. I mean, it's one of the first things that I think new technicians should be transitioned into is thinking of every pressure that you take is really just correlating to a temperature. It has a temperature meaning because then you can start to make sense of temperature readings alone, which is what Jim and I have talked about a lot on the podcast about checking your system without taking pressure measurements on every single case. And that's something in refrigeration you see all the time. I mean, you're not always connecting gauges to a piece of equipment, correct?
That is correct. There's a lot of times you're not going to. We're talking about Jim Bergman. I will also say that he had a great point that he made, something that we all think, but you really need to understand. You have no business attaching service gauges to anything if you do not know what those pressures are supposed to be before you put those gauges on there. And I'm not talking just pressures. I mean, saturation temperatures. You need to understand if this particular box is going to have a 20 degree TD, 25 degree TD, your pressure should be about this. So that way, when you connect them, you're not looking at them going, I wonder if those pressures are correct. And that applies to air conditioning and refrigeration.
So rubber meets the road when we're talking about a TD. If you're looking for a TD of 20 and you have a box temperature of 40 degrees, then that means your suction saturation, your evaporator temperature that you're measuring on your gauge should be about 20 degrees.
That would be accurate. Now, I will also say that a lot of times we do not know exactly what those TDs should be because refrigeration manufacturers sometimes beat to the tune of their own drum. And it seems like they make things up on the fly. Their refrigerators work, but a lot of times, even when I'm talking to technicians or guys that are working with me, I hate this word, but I do use it as we use a rule of thumb. I have a general idea that my TD should be somewhere within 20 to 25 degrees, somewhere in there. There's no specific documentation saying this is what it should be. We're unlucky. I tend to think that we have a little more accuracy when it comes to some air conditioning systems because some manufacturers do publish what the subcooling should be or what the superheat should be or the target superheat should be. Refrigerators, we're not very lucky, especially when it comes to reach-in refrigerators. The manufacturers tend to kind of hold some of that information.
Yeah, and today we're going to focus more on the reach-in side, and it crosses over into walk-ins for sure. At least some of what we're going to talk about, but we're going to stay on the simple side. Obviously, when you get into grocery store refrigeration, parallel systems, then your controls are going to tend to get more complicated. I wanted to start with exactly what you already covered, which is there are a couple things you need to think about. You need to think about the temperature of the box, and you need to think about the temperature of the evaporator coil. And those are two things that you need to understand first and how that even relates to pressures before you get started. And that specifically applies to this first control that I want to talk about, which is the standard pressure control, just the basic, simple pressure control. So how does that work?
The basic, simple pressure control in its infancy is just a control that it can either open or close when the pressures fall or rise. The standard low pressure control is going to open on a pressure fall and then close on a pressure rise. We can use it as two functions. We can use it as a loss of charge switch. So if the pressures get so low because we're running out of refrigerant for some reason, it can open and shut the system off. So it can be a compressor protector, or we can use it with the idea of a temperature differential from the evaporator in mind. We can use it as a temperature controller because if we know that at a certain temperature, let's just use R22 refrigerant, R22 refrigerant is going to be this pressure at a certain temperature. Well, with that logic, we can control temperature that way. We can say, hey, if the box is running and the pressures are this much on the low side, this control, we can set it to do whatever we want it to do. And therefore, we can use it to control temperature.
And so that is that basic connection between pressure and temperature. And we're specifically talking on this kind of control scheme side, mostly about the low side of the system, right? We're talking about the suction side.
That is correct. I'm going to say typically because I'm sure there's some weird situation, but typically we're going to control the temperature by monitoring the low pressure side of the system.
As an example, you mentioned an R22 system. And so in that case, if we wanted it to shut off at a 20 degree evaporator temperature, then that correlates to a 43 PSI pressure setting then. But how do you set, because of course it doesn't come on and off just at a single temperature. So how do you set that differential? How is that set up?
Well, first off, something we have to understand when we're using a pressure control is pressure controls are never 100% accurate. They are actually very inaccurate devices. Oftentimes, they will have a number on a little readout or a dial on the control that says 20 PSI, 30 PSI, or sometimes they're a differential control where it'll say cut in, cut out minus differential. Those numbers are never set in stone accurate. The only way to know if it's accurate is to field calibrate the control. Typically the easiest way is to use some nitrogen, apply so much pressure to the control and write down when it's set at 20 PSI, where does it actually turn on and off at and record those. So then that way you have an idea of how accurate the control is.
And that is critical, not only that you don't trust your control, but also that you don't trust your tools. You did a really good job of showing how you calibrate even your K-type thermocouples using an ice bath in order to make sure that they're measuring what they should measure before you rely on them to measure box temperatures. Talk a little bit about that.
That's a pet peeve of mine, in that people tend to rely on their digital gauges. Let's just talk about a K-type thermocouple clamp that you're going to use to measure, let's just say, suction line superheat. It's really easy for people to just throw those on a system, pull the insulation back, clamp the clamp on there, and hey, my service gauges say that that clamp is measuring 45 degrees. Well, there's a couple things you have to think about. Number one, K-type thermocouples tend to be very inaccurate if they're not calibrated properly. Okay, so in all reality, we should be calibrating those every time we use them. Now, in a perfect world, that's not going to happen. Me personally, I like to calibrate my thermocouples at least once a week and verify their accuracy. The next most important thing that I can't stress enough is that once you calibrate a thermocouple to a port on your thermometer or your gauges, it has to stay in that port. And when I say stay in that port, you can unplug it, but you have to plug it back into the same port again. It is calibrated for that port only. You cannot plug it into the liquid line side of your gauges or the T2 plug on your thermometer without calibrating it again. So that's very important, is checking the accuracy of our measurement devices.
Yeah, because when you're making an adjustment to the K-type thermocouple, you're not actually making the adjustment on the K-type thermocouple. You're just adjusting your meter or thermometer or gauge or whatever it is, so that way the K-type thermocouple reads correctly. And this is a really common thing that you see guys do. They'll have a T1 and T2, say, on a really nice quality, say a Fluke 2-channel thermometer. I had one of those a long time ago, or even a field piece or whatever the case may be. And then they pull them out, and when they reconnect them, they swap them around, and now they could be wildly off. And so for this type of stuff, especially in refrigeration, where you're really trying to hit it to the degree as much as possible. I mean, you don't want to be 2, 3, 4, 5 degrees off in a lot of cases. You need to make sure that the measurement devices you're using to confirm your settings are correct. And then, like you mentioned, because these things are historically inaccurate, you can't just set it and forget it. You've got to set it and make sure that it cycles on and off at the correct temperatures. Talk a little bit just from the standpoint of refrigeration. What kind of things do you do after you do set up a control to make sure that it is going to work properly before you leave?
As in verifying that the box is coming down to temperature? Is that what you're asking?
Yeah, just meaning like, because in air conditioning, for example, we'll talk about like make sure that the drain drains and make sure that the equipment is running when you walk away from it and that sort of thing. But in refrigeration, generally, we want to be a little more careful to actually watch the thing come down. You don't want to just take a hot box, set it up, confirm, you just set the dial and leave. You want to be a little more thorough in making sure that all the controls, defrost, everything is all working before you walk away from it, right?
Yeah, definitely. So after I set up a control, typically, now this is me personally, I am going to watch that box operate. Now, if I felt the need to put service gauges on the system, again, that's a very important designation. If I felt the need, I am going to watch the pressures, watch the system operate, and I'm typically going to watch it satisfy and then turn back on probably 2 to 3 times. So I'm going to watch a full cycle on the system to see the actual cutout temperature, so the temperature at which the system shuts off, and then the cut-in temperature at which it turns back on. And I'm going to watch that 2 to 3 times.
And that's what I was going to suggest, is that you want to at least watch the thing cycle once before you walk away from it. Because I've seen a lot of guys do this, and it's kind of a standard way of doing it, where when you're setting up a control, you kind of cycle it on and off, and then you test it against what the actual temperatures are. But you driving a dial up and down isn't the same as allowing it to actually cycle naturally. And especially when you're talking about analog controls, your basic electromechanical controls or pressure switches, they can be very, very inaccurate. So you want to make sure that it's set in properly. Which brings me to the next type of control. So we talked about the standard basic low side pressure control, suction pressure control. Now what is the next option? There's something called a constant cutting control. How does that work?
On the low pressure control, once we've verified that it's accurate or we've compensated and made it accurate, we're always going to want to understand that the way when we're using it to control temperature in a system is that we're going to keep the evaporator TD in mind when we're setting up the pressure controls, but that you also want to account for line set length and how the system's operating. And what I mean by that is let's say we have a remote condensing unit that's on the roof and it's got a 75-foot line set. You really need to watch that box operate. You cannot just set it and forget it, because I bring up the way to set up a pressure control as a temperature controller by using the TD. But when you have a long line set length, you're going to have pressure drop that's going to become part of the equation. You're going to have a lot of factors inside there. So it's very important that we monitor the system, and there is going to need to be field adjustments. You can actually find on some of the old school literature from Tecumseh, you can find an old pressure chart that'll actually tell you if you're using, when I say old school, a lot of the information is going to be for R12 or R22. It's going to say if you're using R12 and you want the box to be this temperature, here's the pressure control settings. That's just an easy way for someone to do it. They're basically just doing the math for you. But those settings kind of go out the window when you have a long line set length. So that's something always important to remember is that you have to watch the box operate. You can't just set it and forget it. You really got to fine tune things once you install them.
Yeah, exactly. And also, and again, we're talking about smaller systems here, but then you also have to consider with some of these types of controls, you're actually working with a pump down solenoid, and then that even adds in a whole nother thing. And that's, again, we're not to that point yet, but you talked about length of line and refrigerant capacity and all these sorts of things. You really have to make sure that you know the type of control scheme that's being used and that it's set up properly and that you test it and make sure that it is functioning before you walk away from it.
And that is correct. And I would also say that even in the article that I had written, the pressure control used as a temperature controlling device is not very common anymore. There's only a few instances. I still do see it today on certain manufacturers, but there's only a few instances. It's only on self-contained reach-ins anymore. So the line set length is 3 feet and there's really not too much involved. So they are pretty simple. And when you think from a manufacturer's standpoint, it's really a very easy way of controlling temperature, and it's very economical for them because thinking that we're using the pressure of the system, thinking about the saturation temperatures, and we can use that pressure control as a defrosting device also, because if it's turning the box on at 40 degrees or whatever corresponding pressure that is every time, we brought the coil temperature above 32 degrees, so therefore we've self-defrosted it. So they are an economical feature for the manufacturers. And you tend to see that they're doing that for a reason, to save pennies basically in the long run, because when they manufacture 1 million boxes in a year, those pennies equate to be a lot of money.
One of the big challenges that we always face is there are a lot of ways of doing this, but money does always come into play. So now let's go ahead and talk about the next type of control, and that is the constant cut-in control. And we'll start with just the basic electromechanical control. And this is very, very common control strategy.
I would say the most common refrigerator controller is a simple coil sensing temperature controller, or we may call them a constant cut-in control. Okay, they're very simple in theory. Essentially, you have a sensing bulb that is embedded in your evaporator coil. There's a couple different methods of doing that. And that control is directly sensing evaporator temperature as close as it can without being a pressure control. So they've got the sensing bulb embedded in the evaporator, and they have figured out the temperature difference between the surface temperature of the evaporator and the internal refrigerant temperature. They've done the math for you. But that control is monitoring the evaporator temperature. And what it does is it basically just turns the system on and off. Instead of using air temperature, it essentially just uses evaporator temperature. And it's a little bit more accurate, in my opinion, but there's a problem with it. Number one, it's very susceptible to the system operation, the system vital signs. Your evaporator superheat has to be absolutely perfect for a coil sensing temperature controller to work with. A lot of technicians I hear and people that I talk to seem to say those controls are no good. I don't like those controls. They're always faulty. There's always a problem with them. Well, we can step back and think about it. Those controls are actually very accurate controls and they work really well. But a lot of things can affect the way that those controls work. If you have a dirty condenser, your temperature controller is not going to work right because your system operates as one whole piece. So if you've got high head pressure, it's going to affect the evaporator temperature and so forth. If you've got low refrigerant charge, that coil sensing temperature controller is going to see that before you do typically, before things start happening. So you're going to get a service call about that temperature controller or about that box. And you're going to say, oh man, the box is not turning on until it gets to 43 degrees. Well, it might not be the control. So they are very accurate and they're very good controls, but they can be very difficult to diagnose.
Yeah, and the system needs to be working properly. I mean, they rely on the system functioning properly for them to function properly. And in one sense, I think technicians would say, well, that's a problem. They should just do their job. But if you think of it in a broader sense, if there's a problem with the equipment, then you're going to need to fix it anyway. So really, what's the issue? So where in the evaporator coil do you want that coil sensing probe to measure? Is it just anywhere in the evap coil, or is it a particular place?
This is another interesting point. Manufacturers tend to beat to the tune of their own drum, like I've said before, and they kind of all differ in different ways, okay? If you ask my opinion, I typically want it to be closer to the outlet of the coil, so you're seeing the full function of the coil. You're seeing the refrigerant go all the way through the coil, and you're sensing the temperature of the refrigerant as it's leaving the coil. So then you know that this has happened inside that coil. But I have seen other manufacturers do some weird things where they put the sensing bulb in the front of the coil. They kind of all have their own theory and way that they do it. The important thing is to remember is that that system has to be working 100% correctly to the way that the manufacturer designed it. Now, that is also another point of contention, because if we don't know exactly what that thing should be doing, how do we know how to diagnose it?
Right, and it does make it challenging. And you and I actually had a conversation about this, sort of the theory of this setup after you wrote this article, because I was having some struggles with it. But what it comes down to is a lot of these electromechanical kind of basic coil sensing controls, they don't have necessarily even temperature gradations on the control. It just has like numbers in some cases. In some cases, just like dots on it. There's not a whole lot of information on that dial. And so where my mind works, I'm used to thermostats. So I think I want to set this box to 40 degrees, and that's what I want the box to be. And this control should do that. This control is specifically set up for this equipment because a particular coil temperature relates to a particular box temperature, as long as everything's working properly. As soon as you kind of upset the apple cart and things aren't working properly, well, now everything can be off, and it may not do what it's supposed to do. So it is important, like you mentioned in the article, that it's important that you have the right control for the manufacturer when you have these simple controls, because if you were to put in a different control, then it may not be set up in the same way, not designed in the same way, and that can be a problem. And that's one factor there. And on the other side, you got to make sure everything else in the equipment is working properly, the superheat set properly, the system is clean and well functioning.
That's correct. These controls you had mentioned that a lot of times they have dots or numbers on them. Again, this is going to be a general rule of thumb. I kind of cringe when I say that, but the controls typically have numbers on them from 1 to 8 for the most part. That's pretty common. Most manufacturers, that control should usually be set between 2 and 5. That's typical. That's the starting point. I sometimes go in the middle somewhere, 3, and start there. But again, it's not one of those things you can just set and forget. You've got to watch the box operate. A lot of these systems too, I will say that they can be difficult to diagnose when they have a constant cut-in temperature controller or a coil sensing temperature controller, because let's add another factor into there. A lot of times the refrigerant charges on these are very minimal. We're operating with 1/3 horsepower compressors or condensing units, and the refrigerant charges can be as low as 6 ounces. So they purposely don't come with service ports on the system. They usually have process stubs. So basically it's just a port coming off the liquid line dryer that's welded shut. So before we tap into that system, we have to really evaluate the entire system to make sure that we actually need to put service gauges on that system, because we can run into some problems if we go put a gauge with even a 2-foot hose on it. We could lose a lot of refrigerant when you're dealing with 6 ounces. So that is an argument to be made for smart probes or small service gauges.
Yeah. And again, I mean, a lot of what we do in refrigeration is common sense assessment. I mean, Chris talks about this all the time in his videos. He goes through and he's noticing things as he goes. Oh, okay, this is dirty. That needs to be cleaned. The seal isn't good on this door, so on and so forth. And a lot of the diagnosis is visual and common sense stuff. But it does create a challenge sometimes when you're wanting to confirm 100% that it's working properly, and you really don't want to put gauges on it unless you absolutely have to. Let's touch on the idea of constant cut-in and what that phrase means. What makes something constant cut-in?
So the idea of a constant cut-in temperature controller, or we can call it a coil sensing temperature controller, is that it's pretty simple, actually. It's going to constantly turn on at a set temperature. Okay, so most constant cut-in temperature controllers are going to turn back on or cut in between 38 degrees and 41 degrees. The idea behind that is that you are making sure that the coil temperature is 38 to 40 degrees or 41 degrees. And if you understand how a refrigeration system works with the TD in mind, my evaporator temperature is going to get well below freezing. So with a constant cut-in control, what we're actually doing, we're maintaining the temperature in the box, but The second thing that it's doing is it's making sure that that evaporator coil is clear of ice before it turns that compressor back on. And that's important to understand because as that system operates, again, if we have a 20-degree TD on a box that's running 40 degrees, that evaporator temperature is going to be 20 degrees when that control or when that system is running. Okay, obviously 20 degrees is below 32 degrees, which is our point at which we're going to start to build frost on that coil. So if we don't have something to defrost that system, we're going to start to build up ice. And slowly over time, that ice is going to make the box stop working. So the constant cut-in control actually serves two purposes, and that it controls the temperature of the box, but then at the same time, it's a self-defrosting control. It ensures that there's no frost buildup on that coil every single time that compressor turns on.
Again, make sure that everybody who's listening to this, you want to know that when we're talking about this strategy, we are talking about refrigerators. We're talking about refrigerators, coolers. We're not talking about freezers at this point because we're not talking about a defrost strategy where you have heaters and those sorts of things. We're talking about just off-cycle type of defrost here. I think a way to think about this, when you hear constant cut in, so that means that the cut in is fixed. It's constant. It doesn't change. You can move the dial and you're not changing the cut in. So that means that when you move the dial, you're changing the cut out. So it's constant cut in, variable cut out, depending on how you set that dial, right?
That is correct. You can also call that your differential of the temperature controller. But yes, that's exactly what it is. So I like to try to tell people that no matter what you do to that dial, I even tell customers this because a common service call is I keep turning it colder and it's not getting any colder. We can also relate that to an air conditioning call at a residence too. But like I tell the customer, don't turn the dial. Because that particular refrigerator has a constant cut-in control. So if it's not working, there's something wrong. Turning that dial really doesn't do anything. For us as technicians, we can tweak some things by turning that dial. Essentially, by turning the dial, we can increase or decrease the start and stops of the compressor. Because if we can turn the dial colder, then we can make the compressor run longer and we have less start and stops on it. But there's a fine line there.
Then there's also digital controls that do similar things. So how do those work? What are some differences?
So one of the newer strategies that we have coming into the market, and this has a lot to do with energy efficiency requirements by federal government, is that we have got a new type of temperature controller, and that is, I call them a digital constant cut-in control. We have those controls, they're OEM controllers, and they typically can do a broad range of stuff. They can still be a constant cut-in control. They'll have two sensing probes. They'll have one for the air and one for the coil, and it will still operate as a constant cut-in, so it's looking at evaporator temperature, but it'll have a second probe that we can do all sorts of features with. We can see air temperature, which can help us with defrosting. We can have really the sky's the limit because if you have a computer programmer, they can program that control board to do just about anything.
We've talked a lot about the ERC-213, which is a Danfoss control, kind of a universal refrigeration control that can be used in a lot of different applications. A lot of different defrost strategies are available to that control, but there's a lot of similar controls made by other manufacturers. But the one thing that you'll start to see as soon as you get a digital control is that you, as the technician, start to become responsible not just for a dial setting, but also for those temperatures. And that's where a deeper understanding of that temperature difference, that design temperature difference between the box temperature and the evaporator temperature becomes more critical. Whether the manufacturer tells you or not, if they don't tell you, then you sort of have to make a good guess at it or your best guess. Because otherwise, again, you're still sort of just doing trial and error a little bit. You're testing it on off in order to get the box temperature that you want and to set up the defrost strategy that makes sense. But when you're dealing with a digital control, you're actually looking at a readout that gives you numbers versus just some numbers on a dial that really don't have a deep meaning.
So on these digital controls, I want to point out that they have some weaknesses, but they also have some really good things about them. Okay. One of the things that I really like about the digital controllers is we're no longer looking at a number on a dial. We're looking at a digital temperature readout. So that can be very beneficial for us because it can be easier to diagnose. If we can see that that control is turning on when it's this temperature in the box, then that helps us to diagnose them a little bit better. That is definitely a plus. Let's just say this is a plus. Some of the other things we can do with these digital controls is because they can program to do just about anything, they can cycle evaporator fan motors on and off to quote unquote save energy. But at the same time, there can also be some weaknesses in these controls. And I'll say the number one weakness in a digital control is the sensors or the thermistors. All manufacturers of every control are having a very difficult time making sensors or thermistors that are not susceptible to water intrusion. Okay, and I'm not talking dipping in a bucket of water and they fail, but if we've got a sensing probe that's mounted in the evaporator coil and that evaporator coil has frost on it all day long, that sensor is around that moisture and the moisture intrudes into the sensor and becomes a problem. So I would say one of the number one weaknesses is bad sensors. That's a huge thing. And on the digital controls, I think oftentimes they're diagnosed as being bad when in fact it's just the sensors. Now, another issue that I run into with the digital controls, and this is also, you can call this a good thing about them too, is that they can have actual defrost built into them where they actually have a timed defrost. So that could be a good thing because not only are you looking at coil temperature, but on top of that, the unit basically, it can be programmed by the manufacturer, but typically 6 times a day, it looks at the coil temperature and it says, hey, I don't need to defrost, or hey, I do need to defrost. So it can actually skip defrost and just keep running. But at the same time, a problem is, especially in restaurants that have a very high volume, is that sometimes we need more defrost than that controller can handle, or sometimes we need longer defrosts. Typical strategy in a restaurant is to defrost for 45 minutes in the middle of the night when nobody's there. So that way we can really clear that coil of ice. On one of these controls, they typically don't have the ability to do that. Typically, whatever defrost it uses, it applies that same defrost time to every single defrost. So you typically set it up for a 5 or 15 minute defrost. You typically can't set it up to do a 45-minute defrost at a certain time in the middle of the night. So I'd say that's a weakness about these digital controls.
And so when you're talking about doing like in the middle of the night type of defrost, which is an interesting thing to do in a busy restaurant, it makes a lot of sense. You're talking about like with an analog electromechanical time clock, you can go in and set the pins so that way every night at 4 a.m. or whatever, 2 a.m. or whatever the case may be, you can set it so that it stays off for 45 minutes. Is that what you're referring to with that more analog strategy?
Yes, definitely. Again, working in restaurant refrigeration, it's its own little demon. One of the major problems about restaurant refrigeration is the volume of use those refrigerators use. We go through starting components like crazy. Our compressors are run to the bone because they're starting and stopping multiple times an hour. On a residential air conditioner, you can set the thermostat to say, hey, I don't want that compressor to start more than 3 times an hour, 5 times an hour, whatever it is. Without knowing for sure, I could tell you right now that within an hour period, my refrigerator's compressor is going to turn on probably 10 to 15 times, on and off, on and off. So we tend to have problems with evaporator coils freezing up on these refrigerators because the reason why they're turning on and off is because we're opening and closing doors and drawers, and we've got a lot of intrusion from outside air. So these things are running hard. And oftentimes we have issues where even with a constant cut-in control, just a standard electromechanical constant cut-in controls, we can still run into freeze-up problems, which is very interesting because you're looking at coil temperature, but you can still have freeze-up problems. So in a situation like that, we might install a electromechanical defrost module that I can say, hey, at 2 a.m, I want this thing to defrost for 45 minutes, to where it turns the evaporator fan motors on and it just shuts the compressor off. Now, it's important we do that in the middle of the night. And the reason why I say that is because there's nobody there. And so your product temperature typically isn't going to come up above 40, but we can defrost the thing for a nice long period of time.
You actually get to a really good point, which is when you're dealing with refrigeration that's very active, meaning people are opening and closing the doors and pulling out product and putting in product that maybe isn't all the way down to temperature. Now you just have these constantly varying loads. That's part of the reason why coil temperature measurement is so critical, is that you're measuring on something that has some mass. The coil has some mass. It's got refrigerant in it. It's made of metal. And so it's not going to jump up and down like crazy, whereas box temperature is going to jump up and down. It just is. And I think some people have a misunderstanding that box temperature and product temperature and coil temperature are all the same thing, and they're not. Those are all very independent things. Your product has mass. The actual walls of the box or of the inside of the freezer refrigerator has mass. But then you have the air, which easily can jump in temperature. Somebody opens that door. You remember when you were a kid, my grandpa used to always tell me, if you open up the refrigerator, the penguins will get out. Like all that hot air rushes in, and it can very quickly change the air temperature, which I think is one of the big reasons why it's not a great idea to just be measuring the air temperature alone, because you don't have that thermal mass.
I would even say that I've done some scientific refrigeration work. I don't do it anymore, but in the past, I've worked for hospitals doing refrigeration work where we're cooling medicines. I mean, you could be cooling anything, medicines, vaccines, all kinds of stuff. And in those situations, they actually control the system off of product temperature. So we'll have a vial of glycerin sitting inside that refrigerator that the thermostat is sensing the actual glycerin temperature. And what they're doing is they're simulating the temperature of the product, not even looking at the coil. Well, actually, they will look at the coil too, because they have these controls that run these things are very complex. But they'll actually sense the product temperature to make sure 100% sure that that product temperature never gets above their thresholds. Because a lot of times in the scientific industry, you've got, no joke, a box that has over $1 million worth of product in it. And this is a tiny little box. And to them, a loss on that product is not acceptable.
Yeah, and it's also not acceptable to your insurance company either, I imagine.
Yeah, it was definitely a very, very stressful time. And the reason why the customer, we don't do service for them anymore is because it put the stress on me, including myself. We're a small company, so I have 4 people, including me, that are working. But it got to the point that I had to be the person to go to that hospital every single time. And even on me, I mean, I could work on it, but the stress level was just through the roof because, the temperature's 1 degree above where it's supposed to be. And they would call me out there at 2 a.m. We don't care what it costs. I mean, we could make all the money in the world. It wasn't worth it because it was just too stressful.
Yeah, trust me, I understand the feeling. We're getting into more stressful stuff as we move forward in Kalos, doing more commercial refrigeration, and it is pretty wild. I can only imagine what that's like.
Yeah, I'm downsizing with all that right now. I cut all that stuff out and we're letting go of customers, and I'm actually reducing the stress level, even though of course the money is not great. I mean, don't get me wrong, the money's fine, but I mean, we're basically evaluating the way things are, and stress is a big factor in it for me. So I'm cutting back.
Yeah, makes sense. So what other types of controls are there?
We've kind of talked about a constant cut-in control, which typically tends to be an OEM replacement control, meaning that that's an original equipment manufacturer's control. You can get those on the aftermarket supply houses, but typically you're going to see those in OEM boxes. We've talked about using the standard pressure control as temperature control. That's a kind of an antiquated control, but it still is viable. We've talked about the electronic constant cut-in control. Now, kind of similar to the electronic constant cut-in control, and you've kind of already touched on it a little bit, but we do have a universal control, such as your Dixel controls or your Danfoss ERC213, which you made the video on. That is a aftermarket control. Now, it's important to understand too, just because you see a Danfoss control or a Dixel controller, it doesn't necessarily mean it's aftermarket or it's OEM. They do make specific controllers. Danfoss will make a custom one that you can't go buy at the supply house, and vice versa. Okay. But the universal controls that we can buy at the supply house, they typically are pretty broad. And you kind of explained it in your video when you did that Danfoss control. I mean, the sky is the limit. You can do so much with those controls if you have the mindset and can really think it through. I would caution you to be careful about using those things because you can screw some things up. But if you really know what you're doing, man, you can make those things do all kinds of cool things. Staging evaporator fan motors. You can make them turn on alarms that send signals, that set up auto dial systems that call people when the refrigerator goes down. You could do all kinds of stuff with the universal digital controls. You can also use the universal digital controls for freezer controls also. You can set them up to do electronic defrost. You can pretty much, like I said, the sky's the limit on those. We have other controls too. We have basic electromechanical controllers that sense air temperature. We really haven't covered those ones yet. Those are a very common refrigerator control in walk-in coolers and even walk-in freezers that are simply just a standard temperature controller that you mount in the return airstream, and it does one thing. It just turns it on and off dependent on air temperature. We do see those. I tend to see people using those a lot on reach-in refrigerators when they really, really shouldn't, because when you pull out a constant cut-in control and you put in one of those air sensing temperature controllers, if you don't know what you're doing, which I tend to think that a lot of people don't understand how the constant cut-in controls work, they've just eliminated a defrost out of that system. There's no more defrost in there unless you put in a mechanical defrost timer. So you do have to be cautious about using those air sensing temperature controllers.
Yeah, because with the constant cut-in controller, because you're sensing the coil temperature, you're building in that temperature increase where it's going to wait until, once that thing cuts off, it's going to wait until it gets to a temperature. the fixed constant cut-in temperature, so it does have a chance to defrost. Whereas when you're using an air temperature controller, it's going to cycle on and off like an AC thermostat. I mean, it's just going to go on and off, and it's never going to pay attention to the evaporator coil temperature. And it also seems like with just the air temperature and these more universal controls where they're set up to just measure air temperature, it seems like you're going to short cycle quite a bit more as well.
Definitely. And I can guarantee you, without adding a defrost to that system, you're going to have more freeze ups on that system too. You're definitely going to get a lot more calls on it. Now, they're simple. The simplicity of them is easy. I mean, it's just really easy to know that, hey, when the temperature gets to this thing's going to turn on and it's going to turn off. I really think that we as technicians need to investigate a little bit more and not be afraid of certain things like a constant cut-in control. People tend to bash them or say, oh, those things are horrible. They insert name of whatever manufacturer of a refrigerator. Their controls are no good because they're constantly breaking. But I think that we as people, naturally, we tend to be afraid of change. And a lot of us are actually afraid to ask questions. We're actually afraid to say, hey, how does this work? Can you explain it to me? Because once you understand how those constant cut-in temperature controllers work, they're really simple. Now, they really are complex at the same time. So I guess that's kind of a problem there.
Well, I think it's complex. I mean, this goes back to a meeting that I have consistently with my technicians, but I just had again last week, where it's like, look, making a mistake with how you understand how something works happens all the time. I mean, I've made so many mistakes with things like thinking it's one way and it ends up being another. But you eliminate a lot of those mistakes, and you learn how to eliminate a lot of those mistakes by not leaving until you've fully tested the equipment. And it solves so many problems when you do that. Even if you don't fully understand everything about the piece of equipment, if you just test it every possible way and watch it go through some cycles, then you're going to be much more likely to say, hey, that doesn't seem right. And then you're going to have a chance to rectify it. And of course, with refrigeration, no matter what type of refrigeration you're working on, you have temperature control, which is you want to keep your product, your box at the right temperature. And then you also have to think about defrost. So you've always got to keep those two things in your mind. And as long as you're thinking about both of those things, all right, how's this thing going to turn on and off and maintain the proper temperature of the product? And B, how's the thing going to defrost? And is it going to defrost enough, or is it defrosting too much? If you're constantly thinking about that, well, then you're probably going to eventually come up with a good strategy, depending on the application.
Definitely. My company had a service call recently on a refrigerator not working at a restaurant, and it was not myself that diagnosed it. It was another technician. He went out to the restaurant, and this was a 2-door reach-in refrigerator that was a sealed system, so you could not put service gauges on it unless you absolutely cut into the system. So he diagnosed the system as having a bad temperature controller. The symptoms were, when he got there, the customer was complaining that it was maintaining 44 degrees. He walked up to the refrigerator. He noticed that it was indeed maintaining 44 degrees. He put his calibrated digital thermometer in the box, and he noticed that the box was maintaining 44 degrees. So he diagnosed it as a bad temperature controller. The temperature controller that the manufacturer sent us was a giant digital conversion system. So it was taking out the old electromechanical temperature controller, and it went to a digital control. Because of that, when I saw that control came in, I decided that I was going to be the one to go out and do the conversion, just because it looked kind of complex. So when I first got to the restaurant, I kind of wanted to confirm the diagnosis. So I went through the refrigerator, and I noticed, sure enough, that it was turning on and off at the wrong temperatures, and it was a sealed system. I decided that I wanted to look a little bit further, and I did not put service gauges on the system. I still did not feel the need, because I noticed something when I opened the door of the refrigerator. Again, this is because of experience. The evaporator fan motor wasn't making the right sound to me. The sound level, the humming sound that it was making, just didn't seem right. And further investigation, I kind of looked at it a little bit, and I noticed that evaporator fan motor was not spinning fast enough. So let's think about that for a sec. This unit had a constant cut-in temperature controller. The evaporator fan motor was not spinning fast enough. Therefore, my evaporator coil was getting colder than it should be, and it was staying colder longer than it should be. So the temperature controller actually wasn't the problem. The problem with the unit was that the unit had a bad evaporator fan motor. Once I changed that evaporator fan motor, put the right one in there, the fan motor speed sped up, and that temperature controller, the existing one that was in the box, was now regulating the temperature of the box the correct way. It was turning it on and off and maintaining 40 degrees inside the box. Now, I wasn't upset with the technician that made that diagnosis. It was definitely a learning experience, and I actually made a video on it because I think it's a great learning experience for everybody. Sometimes it just takes personal experience to know how these boxes operate. Now, if I would have tapped into the system and put service gauges on it, I definitely would have seen the problem because I would have seen refrigerant pressures that weren't accurate. I would have seen that my coil was getting too cold. But this is one of those systems that has a very small refrigerant charge of, I think, 16 ounces. And I was afraid to put my service gauges on it because I didn't want to lose any of that charge and cause a problem. So it's very important that when we're diagnosing these things, we really look at the big picture, think about it, check our vital signs. And also when we're working on them, even when we're not working on an evaporator fan motor, when I'm opening and closing that doors, I'm being vigilant. I'm using my senses. I'm paying attention. It's a very important thing to remember. Wearing headphones when you're working in these restaurants, when you're doing a preventative maintenance on the roof, when you're working on an air conditioner can be a problem. Because if you're not listening to the sounds and paying attention to what's around you, you can miss things. And at the same time, just listening to those sounds day in and day out gets you used to it. So when I opened that refrigerator door, I was like, wait, something's wrong. That evaporator fan motor doesn't sound right. I don't think it's spinning fast enough. So that was a potential problem that I was able to solve and not have to put that control in that customer's refrigerator. Because had I put that control in there, I wouldn't have been able to charge the customer. Because even after I put the control in, it still wouldn't have worked.
Yep. What I'm hearing is the main message is that you're no longer allowed to listen to the HVAC School podcast while you're working because you have to listen to the equipment instead. So thanks, Chris. I appreciate that.
Yeah, no problem.
My entire audience. No, it is a good point. Now, again, you're working in a motor room, something like that. It's so noisy in there, it's probably not going to make any difference. But yeah, you need to pay close attention to all of these things because a lot of guys, when I tell the type of story that you just told, they'd be like, well, how do I know what noises are normal? And how do I know if it's running fast enough? How am I supposed to tell that? It's like a lot of it just is experience. And I know that that's such an awful answer, but sometimes you can prevent a lot of problems just by using your senses and being attentive to your work. Tools aren't always the solution to every problem. They certainly are helpful and they're necessary to know how to use and they're necessary to have. But I notice it seems like even more so in refrigeration, especially in the small stuff where you don't have the advantage of always being able to connect your gauges or it always being a prudent idea to connect your gauges, that your senses really do make you a much better refrigeration technician if you're very, very attentive.
I kind of said something earlier that it's simple, but it's complicated. It can be complex sometimes, and sometimes we can't teach experience. And we wish that we can teach by our mistakes, but unfortunately, I think sometimes people have to make those mistakes. And that is a bummer because as a business owner, I don't want my technicians making mistakes. I want them to learn from my mistakes, but the struggle's real, I guess.
That's what it comes down to. All right, so if anybody wants to learn from some of Chris's mistakes, then the best way to do that is through video, of course, because you can actually see them live and in living color. So you can go to HVACR videos on YouTube. Is that correct?
That is correct. The icon is a little cartoon picture of my face.
Yes, I've noticed that. It's a real cute little picture of Chris. So you look for that. Thanks for coming on the podcast, Chris. It's a pleasure. Just full disclosure here, I accidentally stood Chris up last time we were supposed to record this, so my bad on that, but thank you for coming back on. Chris is a very important part of the HVAC school community from the very beginning. He's always been very helpful, and I really appreciate everything that you do for the trade, so keep it up.
And the same goes to you. I really appreciate what you do. You know, the HVAC school is really beneficial to even my technicians. They read the tech articles, they ask me questions about them, so they get a lot of beneficial information from it too. So thank you to you.
All right, man. Kumbaya. Appreciate you. And hopefully we'll have you on again soon.
Thank you very much.
Hey, thanks for listening to the HVAC School podcast. We've got some big news coming up. We're going to be releasing a new app on both Android and the Apple Store. What do you call that? I guess you call that the App Store. You'll be able to find the new HVAC School app very soon. It's going to have all the tech tips searchable, all the podcasts searchable, podcast player right there, some of our special tools, and pretty soon we're even going to have our forum up there. Basically putting everything HVAC School related right at your fingertips right there with an app, so you don't got to go searching around the old interwebs. So I think you'll find that pretty cool. But in the meantime, you can always find all of our tech tips and podcasts and videos and all that stuff at hvacrschool.com. You can also find out some of the other podcasts that are in the Blue Collar Roots Network by going to bluecollarroots.com. You can discover some of those. So the other day, I was just standing outside, and this girl walks up to me and says, "Hey, didn't I meet you at my vegetarian restaurant?" And it was weird because I never met her before. Never met her before. All right, we'll talk to you next time on the HVAC School Podcast.
Thanks for listening to the HVAC School Podcast. You can find more great HVACR education material and subscribe to our short daily tech tips by going to hvacrschool.com. If you enjoy the podcast, would you mind hopping on iTunes or the podcast app and leave us a review? We would really appreciate it. See you next week on the HVAC School Podcast.